Everyone is talking about generative AI nowadays, but how do these systems actually work? I coded and trained 4 different techniques on the same datasets to compare the results. In this video, we're going to do a quick walkthrough over all the methods, how they work, what their limitations are, and how their outputs looks like. For this video, I went ahead and found this very nice dataset of 16 by 16 images that are pixel art images for games. These contain stuff like characters, props, items, and so on that we're going to use to train all our models on the same data. The dataset includes 89,000 images, all of the size 16 by 16. For the AI models, we're going to use the same models that I talked about in our episodes on AI creativity. We're going to try autoencoders, variational autoencoders, generative adversarial networks, and diffuser models. The goal is to go over each model, show how it works, explain it briefly, talk about its limitation, and then explain how the next iteration improved on it and got better. So let's jump right in. We're going to start off with autoencoders. Autoencoders are models that learn to take in a sample data, let's say an image, and compress that data and then recreate it based on the compressed value. The idea is that you can take an image, let's say 200 by 200 pixels, and then resize that image into a 10 by 10 image. And then if you give the model the 10 by 10 image, it will recreate the 200 by 200 image as good as it can. This very trivially can be used for compression, where data can now be compressed into a smaller size, which a lot of AI models are actually using to compare to different information. So for example, a lot of the facial recognition models take an image of one face, use autoencoders to encode it into a small dimension, and then use the small dimension to compare it with images in the database to know which face it's closest to. This is called one-shot classification and is used in a lot of methods. The idea is that the model starts by an encoder and a decoder architecture. The encoder model takes in the input image and resizes that image into a smaller vector. This small vector contains the information that the model thinks it needs to reconstruct the image back into what it used to be. The decoder then takes in that encoded vector and decodes it back into the original image. So basically, this could be trained in a supervised way where the input image in itself is the label, and the model just learns to go over every image and construct from the input to the output as it is. And when you're done, you can now decouple both model and use only the encoder to encode the data into a small vector size and decode it back into the image again. For our training here, I did the same exact thing for all of them. I made sure that the small vector size is 8 by 8 for all of them. So it's one channel grayscale image of 8 by 8. This is actually flattened into a 64 vector, so a list of 64 numbers that the model can use to generate new information. First, we can look at what the model sees before it trains. Now, the image is reconstructed into something that is very random because the model has no idea how to encode useful information yet, and the coder has no idea how to use this information to reconstruct the image. And this is why it's random before and after. But then after training it for a while, we would see now that the reconstruction of the data looks as follows. It looks very good, where the input image is now constructed into a latent vectorization, which to us means nothing, but to the model means all the information it needs to reconstruct it. And when the decoder model takes that reconstruction, it generates the input image exactly as it is. Now, when you try to take that encoding and generate a new random vectorization, something that is not based on an image that you have, but a completely random vector, and generate new information, this is what you get. The constructed images here are very random. They don't really look anything like the data. But why does that happen? The issue here is that the model generates a latent dimension, let's say 64 vectors in this case, but not every number from, let's say, 000 all the way to 64, all to whatever the highest value is, not every value on that vector generates a new model, a new image. So basically, the problem here is that when you're generating a random vector, you don't make sure that this random vector will definitely give you an image. But then if this isn't used as a generator, what else would I use it for? Well, it does have a lot of other uses. So for example, we talked about compression, where now you can have something as, let's say, lossless as possible to compress it into a smaller dimension, and you can use that to compare it to other information. So you can use it for retrieval, but you can also use it to denoise items. And this is what have been mostly used for autoencoders when it first started. You see, if you give the model input data that you train it on, this data contains no noise. As such, the features that the model learned to extract are always noiseless features. So when you now give it an image which has noise in it, the feature extractors learn to kind of ignore these noise. And then when they're reconstructing the image again, they reconstruct it without the noise. This can also be used to reconstruct images when missing information exists, because the model kind of learns to infer some of the missing information based on what's around. But this makes it unable to generate new content just based on very random data. Now, in order to beat that, variational autoencoders were introduced. Now, variational autoencoders are almost exactly the same to autoencoders, all but one small difference. You see, variational autoencoders also include an encoder model and a decoder model. It also learns to encode the model into a small latent vector and then reconstruct from that vector, but it's a bit different. You see, instead of trying to memorize for every image one latent dimension that will only reconstruct one output image, it kind of learns a distribution. It tries to learn the entire pattern of the dataset so that every input image, instead of being just one value, it's an entire distribution. And that entire distribution is memorized as the mean and the variance. So, what is the center of the distribution, and how far away are the points from that center? And learning that distribution now means that there are multiple values that might include the same image or images close to it. So, before training, when we just enter the model without any training at all, we see the same as autoencoders. Now here I'm showing the vector dimension, the latent dimension, as an 8x8 image. However, you have to think about it as mean and variance that we used to recreate or parameterize into a latent vector that is now 8x8. The mean and vector are both 8x8 vectors. So they're both 64, and then you create from those a 64 item vector that the decoder sees. But for now, just think about it that this 8x8 image is what the model uses to recreate the image once more. Now here the same thing happens, they're both random, but after training we get to this, where we now see that the model is again able to reconstruct from the input image the output image exactly the same. But now what we can do is that when we enter a new latent dimension, we can generate images that look like this. These are way closer to the distribution and much better represented than the one we saw with autoencoders. But there's also something more you can do. You see, now because the output is not just one value, it's again a distribution, you can now interpolate between different values, which means you can now have, let's say, two images and interpolate from the first image to the second image, where every value in the middle is a value between these two images. And you don't have to stop at 2. You can also do it with 4. So now every input, every value on that grid is a value between these 4 images on the corner. And you can do that with a lot more, because now the values aren't just random, they're a distribution. And almost every point on that distribution will result in a good output. Now, the problem here is that the models, when they generate a new image, they are not very crisp. This is because the image goes all the way down and then reconstructed all the way up. Some information is lost. That means that the generated outputs at the end are often blurry and not really crisp. This is also amplified by the fact that the models, the images are very small. So at 16 by 16 pixels, there is really not that much room to see error, so that the images, when they're mistaken, they're kind of looking wrong, let's say. This also happens because variational autoencoders are made to be safe and average. They kind of learn the entire distribution of the data set and not an equal value. This makes them really good at learning structure, but not really good at recreation or generating something that is crisp. And this is where generative adversarial networks, or GANs, were created. They were made to be better than this. You see, the way it works is that they don't really learn to compress and then reconstruct the image. They learn to generate something new from entirely random data. Basically, it's a model that takes a completely random vector and generates an image that is based on the learned distribution from the dataset. And the way that this generator model learns is by using a different model. The other model, called the discriminator, learns to look at an input image and decide, was this image generated by the generator or is it part of the dataset? And then this output, what the discriminator says, is what's given as a feedback to the generator model. And basically, the generator model, as a goal, only learns to fool the discriminator so that the output generated by the generator is sought by the discriminator to be part of the training data distribution. They're sort of in this constant battle where the generator model learns to generate an image that the discriminator model doesn't know that it was generated by the generator. Eventually, the discriminator model gets better at figuring out which images are generated by the generator, and then the generator needs to produce even better images. This, in a way, makes up a generator model that learns to generate data from the dataset without even looking at them, like not directly. It only sees the feedback from what the discriminator says, because the discriminator says, given like say a value, a loss value, gives a metric for how different this data point is to the training data distribution. And now we can use this metric here for the model to say, okay, then I need to change by this amount. And then doing that a couple of times, the generator model learns to generate images that are very close to the training data distribution just based on that. However, even with how cool generative adversarial networks are, they come with a lot of limitations. They are very hard to train. You see, one of the problems is that since the generator model and the discriminator model are always training together, if one side gets too good, the other side doesn't learn anything anymore. For example, if the discriminator is too bad and the generator is too good, the generator feedback doesn't give any meaningful information to the generator. Likewise, if the discriminator is way too good at identifying out of distribution images, the generator finds it very hard to keep up generating something meaningful. What ends up happening is the generator might find a pattern that is good enough to fool the discriminator but has no relation whatsoever to the dataset. It could also only learn to generate an image, let's say just one image from your dataset, that fools the discriminator every time, so it never learns to generate anything new. This is called mode collapse. This actually happened to me when I was training this model. I tried so hard to get the model to actually learn and generate something meaningful, but I kept ending up with stuff like this, where the model would just keep trying to learn some pattern that fooled the discriminator to get a good enough loss, but it wouldn't really get to anything good. What kept happening is that the discriminator was getting good very early on, while the generator was just getting worse and worse as the time went on. I tried so hard, but I wasn't really able to get anywhere. The closest I was ever able to do was right there, where the image isn't really part of the training data. You would see it's very much weird. There's just a blob forming, but it wasn't really a picture. And after doing this for a bunch of time, I actually gave up because I really wanted to get the video out and I didn't want to wait too long, so I ended up scraping it and moving forward. But this just shows some of the issues that you face when you're building a generative adversarial network. Now, if GANs do end up working, they also face a similar issue to variational autoencoders, where the image is always, let's say, blurry or unclear. The problem is that the model is trying to jump from a very random input to a very good output in one step. And when you're trying to do that, the model doesn't always generate something that is good. Ideally, when you're doing this yourself, you would want to generate something, look at it, and then refine it for one step, and then look at that and refine it for another step. But GANs don't really do that. They just look at a random input and generate the output in one go. And this causes issues. And this is exactly what diffusers solve. Diffusion models learn to not just generate the image in one go, but rather they look at a noise image and they try to predict how much noise is in that image to go from noise into, let's say, a fully good image. And then they predict that noise. We now can remove some of that noise, but not all of it, and return the new image now with less noise into the model. The model now can do the same thing, remove just a little bit of the noise, and then predict again. And if we do that enough times, the image will start forming. Now, if the process goes on for long enough, the image starts to get more crisp, more clear, and just better. Diffusion models are usually very hard to train locally, given a large enough image or a long enough data set. I couldn't really train it locally on my own machines, but luckily I was able to train it on Google Colab. We can again look at some of the images that were generated by the model before it learned anything. And as you can see, the model is kind of very random. There is nothing really to see rather than a bunch of random images. This is because the model has no idea what to do yet. So all the generated images are just a bunch more random. And then as the model trains, the model then starts to learn what kind of noise to remove. And doing that for a bunch of iterations, we get these outputs. I would say these look the best out of the bunch. And this is also because these models are intended for generative creation, even for larger data sets. So out of all the models, these are the newer version and let's say the most common ones to use today. They're also used the same exact way for all of the generative AI models that you hear about in day to day, but they all internally work the same. Now, the layers and the architecture of the model can change from one, let's say, diffusion model to another, but the concept remains similar across all of them. And that brings us to the end of the video. So as you can see, all models generate just in different ways. They all have different uses, different ways of working, but they all come with limitations. While diffusion models are great at generating really good pictures, they are very, let's say, slow and they take a lot of compute and they need a lot of resources. And that in itself is a limitation, because if you need to train it on a very large corpus of data set that isn't just very simple, it will take a lot of work and effort to get it running. And with this, I hope that now you don't just hear about generative AI everywhere, you actually know how it works and how to generate stuff with it. I hope this was insightful. Let me know what you think. Let me know if you used any of these techniques before or if you want to. Don't forget to subscribe for more, and I'll see you in the next episode.